Welcome again to the Windows Performance Deep Dive channel. In this video, we deep dive into exposing memory usage via the Windows Heap. Here's a chart that represents how a Windows application typically does dynamic memory allocations, usually through the Windows Heap Manager. The Windows Heap gets blocks of memory from virtualalloc, the Windows-based memory allocator, and then divides them up as requested by the running process. The process might also request memory allocations directly from virtualalloc, or in some apps, via its own custom heap manager. Both the Windows Heap Manager and the base virtual memory allocator have ETW instrumentation, which lets us trace dynamic memory allocations in detail. ETW is Event Tracing for Windows. Today we'll go over the three different ways to track Windows Heap memory allocations using ETW. The first is heap tracing, where you log every allocation in free. The second is heap snapshots, where Windows keeps a database of unfreed allocation. And the third is heap sampling, where you log only allocations which expand the Windows heap. Of the three logging methods, heap tracing is the most detailed and has the highest overhead, logging every single heap allocation in free operation. So it's one of the few modes where ETW does not trace the entire system, but requires you to specify the processes to trace. There are two ways to do this. When the target process is already running, you must use the -process ID switch. You can find the process ID, the PID, using Task Manager, Process Explorer, etc. The other way to specify the processes to trace is by name. When you need to trace application launch, you specify one or more application names using the -exe switch. Notice that in all these traces, if you add the -loop switch to the start command, that creates a circular memory buffer to retain only the last few minutes of the trace. Here's a sample memory chart where a process does 20 heap allocations and 17 heap free operations. We'll use it to illustrate how WPA, the Windows Performance Analyzer, does its analysis. Here we observe three characteristics of the memory usage. Peak outstanding size, the part not yet freed. That's 160 kilobytes at the 22 millisecond mark. The sum size is 290 kilobytes. That's the amount allocated whether or not it's freed. Think of it as the churn. And the impacting size is the end size minus the start size, 56 kilobytes. Here we separate the heap memory allocations into two different categories. The first is AIFO, allocated in, freed outside the trace. Three allocations totaling 56 kilobytes were allocated but not freed within the context of the trace. If an allocation was leaked, it would be one of these. It was allocated but could never be freed. The second is AIFI, allocated in, freed inside the context of the trace. By definition, this chart will always end up at 0. Here's a screenshot of a Windows Heap trace targeting Excel as seen within the Windows Performance Analyzer. Here we can see that the type is AIFI, and there are columns for peak outstanding size and count, as well as sum size and count, corresponding to each point along the stack walk. We've mentioned the size column values, so let's define the corresponding count column values. The sum count is how many total allocations occurred along that branch of the trace. The peak outstanding count is how many unfreed allocations there were when those allocations hit their peak. Let's move on to heap snapshots. To illustrate how this works, let's return to our sample heap trace, which, as you recall, has 20 allocations and 17 frees. We're going to divide that trace into 3 intervals and 3 snapshots. Here are the allocations and frees in the first interval. Then we remove allocations which were freed, leaving the outstanding allocations at the end of the first period. With that, we take our first snapshot. Next, we add the allocations and frees occurring in the second interval. We remove the allocations which were freed from both intervals, leaving the outstanding allocations for the second interval. And we take our second snapshot. And finally, we add the allocations and frees occurring in the third interval. We remove the allocations which were freed from all three intervals, leaving the outstanding allocations for the third interval. And we take the third snapshot. Since this is the last snapshot, if there was a leaked allocation, it would be one of these, since all of the others were eventually freed. Here we visualize each of those three snapshots. These are the allocations which remain to be analyzed, each with a recorded size, thread ID, stack walk, and so on. Imagine now that you want to analyze only the activity from the second interval. Taking the difference between snapshot 2 and snapshot 1 gives the outstanding or unfreed allocations which happened only within interval number 2. Here we see a screenshot of WPA displaying 4 heap snapshots of windward. The 4 vertical bars in the top chart represent the snapshots. In the table in the middle, we selected snapshots 1 and 2. We right-clicked to choose Diff View, which created the bottom table, where we see only the allocations which were added and not freed during the second interval, the second snapshot minus the first. There are 2 ways to capture this Windows Heap snapshot trace. The first is that you use -exe to specify one or more process names, separated by commas. Then TraceHeap captures only the first process to launch with that name and triggers periodic snapshots every 5 seconds, or every 5 minutes with -lean. You can also trigger heap snapshots manually. The second method to capture a heap snapshot trace is to specify the process ID of a running application. You can find the process ID, the PID, using Task Manager, Process Explorer, etc. As we saw before, every dynamic memory allocation in a Windows app ultimately goes through virtual alloc, the base memory allocator. Whenever an allocation causes the Windows heap to need to expand, it gets another block of memory from virtual alloc, which it can then divide up and parcel out. And since we can trace virtual alloc, we can therefore trace heap growth, capturing only the heap allocations which directly cause it to grow. So how does this work? We can trace virtual alloc activity for the entire system using the TraceHeap script as before. Start, stop, and view, but this time adding just the -lean switch. In this trace, we see that Excel, in purple, and Edge, in green, are actively using virtual alloc, with only part of it originating with the Windows heap. So we right-click the Windows heap row for Excel and choose Filter to Selection, which leaves us with a virtual alloc sampled heap activity for just Excel. And for confirmation, here's the full heap trace for the same scenario. And in fact, we see that it has the same general shape and size as what the virtual alloc trace gives us, using much less tracing overhead. I hope you found this a useful introduction to analyzing Windows heap activity. There's more detail in the wiki, in the link given here. You can find MSO-Scripts at github.com/Microsoft/MSO-Scripts. Do try it out and let us know what you find.